Hi, I'm Tom Coughlin, and I'm going to talk to you about changes in digital memory ecosystem that are going to enable the next generation of big data applications like artificial intelligence in data centers, at the network edge, and also in endpoint devices. Now, this presentation uses a lot of material from a report on emerging memories. It's written by me and my colleague, Jim Handy, and I'll talk a little bit about that report at the very end. So here's an outline of what we're going to talk about. We're going to talk about why things are changing, why emerging memories are important, changes in the computing model that's making possible or enabling. We'll talk a bit about these particular memories, talk about who's making these memories, some real life applications that are out there today, and finally an outlook on what's going on in this market long term, summary, and then some references. So let's talk about first why we need emerging memories. So something really interesting is happening in this whole memory market. Although there have always been numerous alternatives to today's leading memory technologies, it's metaphorically waiting outside, trying to get in. They have never had the opportunity that's recently been developing. Until now, these memories, 4 of which we're going to examine today, have been waiting, again, metaphorically at the door, while the market's dominant technologies, DRAM, NAND flash, static random access memory, and NOR flash, have kept them out through their lower prices. Let's look at why things are changing today and why the market has changed in a way that will provide opportunities for new technologies to replace their entrenched competition. Data growth is exploding. For instance, IDC projects that 175 zettabytes of data will be generated annually by 2025. That's up from an estimated 59 zettabytes generated in 2020. Most of this data is supposed to come from IoT devices, and it has the most value when it's processed real time. Think of, say, driving assistance capabilities. And this will increase the need to store and process data in a device or at the network edge to do that fast processing. And probably only a few percent of this data will be stored long term. Greater use of artificial intelligence in devices at the network edge and in data centers is also increasing memory requirements. In addition to the growth of data being processed, the power consumption, as well as latency and data rates, are important considerations in future system design. This leads us to look at the memory technologies which will enable handling this data tsunami. Memory is a big part of server costs, and it must be efficiently utilized to provide the best total cost of ownership. See the figure to the left's example of this. CPUs, memory, and storage have different life cycles and should be replaced separately. This has driven the development and use of pools of similar resources so they can be managed separately. That includes, for instance, memory pools, now using CXL with DRAM, and possibly emerging non-volatile memories as well. In addition, data access and on-chip data movement are extremely costly in terms of energy consumption. Take a look at the figure on the right, you can see that. This is causing systems and data center designers to rethink architectures in order to emphasize data locality and to minimize the movement of data. The semiconductor industry is being forced to change which memory technologies are used in embedded applications like microprocessors, ASICs, and other system on chips. And that's because flash memory, particularly the NOR flash that's used for code storage, can't scale to keep pace with CMOS logic process advances. This scaling limit was a problem with NAND flash. Planar NAND flash stopped scaling at about 15 nanometers. The industry moved then to adopt 3D structures to continue to provide Moore's law type cost reductions. System on chips use NOR flash, and again, NOR flash stopped scaling at about 28 nanometers with the adoption of the FinFET. Some sort of new memory technology is needed to support these chips' code storage requirements, and that's suddenly providing an opportunity for some other technology to replace NOR flash for all processes below 28 nanometers. But it's not just NOR that's heading for a replacement. System on chips using SRAM to store temporary data, and this SRAM is poised to stop scaling, or at least slow dramatically about 14 nanometers. There will be side benefits of these changes. Alternative memories not only scale past the limits of these established technologies, making them cheaper to produce, but they are also persistent and have more balanced read and write speeds, for instance, than flash. This will impact the way systems and software are configured. Now, we're going to discuss these changes later on in this presentation. So this is a chart that Jim and I used to illustrate the issue of scaling. It shows two lines that represent NOR flash and some new emerging memory technology. Process shrinks have been able to reduce costs for the entire history of the semiconductor market. The process nodes run along the bottom, along the horizontal axis, shrinking as we move from the left to the right. Relative cost on the vertical axis has always declined in proportion to each process shrink. But flash memory has a problem, the NOR flash, after the 28 nanometer node. NOR flash, again, is a non-volatile memory the industry uses to store code in microprocessors, ASICs, and other SoCs, and it stops scaling about 28 nanometers. That causes cost declines to cease. So we see that suddenly that line goes straight. The red line goes straight, horizontal. Manufacturers are addressing this issue by migrating to new memory technologies. These allow further cost reductions and follow the scaling law. These emerging memory technologies are represented by the black line on this chart. Although today they are more costly than NOR flash, their cost will eventually fall below that of flash as general process technologies go below 28 nanometers. SRAM, static random access, has a similar problem. Its scaling slows or stops around 14 nanometers. This is a similar chart that plots the cell area for SRAM designs presented at an IEEE conference over the past few years. The cell area on the vertical axis, which is proportional to cost, is on the vertical axis, and the geometry, again, in terms of lithographic size, runs from left to right on the horizontal axis. The cell area has been shrinking to keep pace with the process, but it abruptly stopped shrinking at about 14 nanometers, it appears. In addition, SRAM is much larger than the persistent memory candidates. This leveling off makes SRAM a reasonable candidate to be replaced by some alternative memory technology. The emerging memory will increase the wafer cost over that of a standard CMOS logic wafer, but the die size for some chips will be smaller thanks to the fact that the emerging memory technology will consume a smaller area than the SRAM memory would. This will reduce the cost of these chips, making the design based on these emerging memories more economical than its SRAM-based counterpart. That's going to drive future chips to migrate to an emerging memory as an alternative to SRAM, which is particularly important big data applications where there's a lot of memory, fast memory required on the chip. Now, DRAM is the working memory used in almost all electronic devices, from consumer to industrial applications and also enterprise. Like many semiconductor technologies, it has become more difficult to continue the pace of lithographic shrinks and increasing transistor density than it was in past decades. This figure shows the slowing of DRAM scaling since about 2007. Although there are variations in supply and demand that also impact the cost and price of DRAM price scaling in dollars per gigabyte declined by about 37% annually for about 37 years, until slowing to about 8% annually starting in 2008. Microprocessors of various sorts are used in applications, again, from data centers all the way to wearable devices. Memory, for instance, NOR flash and SRAM, can be a considerable part of the total die space of a microprocessor. If the memory doesn't scale with the lithography on the rest of the chip, it could take even more space and thus be even more expensive. This is, again, driving demand for these emerging memories that can continue to scale and allow you to have a fair amount of memory on the chip, without the chip growing in size. Now, the acceptance of an emerging memory technology depends upon its pricing. This is an important point. To capture a mainstream market, a memory must be cost competitive against established technologies. This cost structure can only be achieved through high volume manufacturing and shipments. Products that don't reach this volume must play in niches because of their higher prices. A good example of that is the 3D crosspoint memory that Intel and Micron developed, in which Intel calls Optane. This chart represents computing's memory to storage hierarchy in a sense. For a memory or storage technology to make sense in this hierarchy, in this log-log scale, it must be cheaper than the next fastest technology on the horizontal scale and faster than the next cheapest technology on the vertical axis. To get that 3D crosspoint adopted into this memory hierarchy, Intel had to overcome a chicken and the egg problem. This new memory technology, 3D crosspoint, must be cheaper to sell in volume, but on the other hand, 3D crosspoint must sell in volume to get cheaper. The same problem stands in the way of other emerging persistent memories acceptance. NOR's hard stop at 28 nanometers, however, and SRAM scaling limits open the door for other technologies to displace them for emerging memory and SoCs. Today, MRAM is a leading candidate in this race. We'll talk more about that. So these changes are going to cause computing itself to change. And there's new developments I'm going to talk about that are going on that involve memory and storage that will be part of those changes. All these emerging memory technologies are non-volatile, by the way, and that brings persistence not only closer to the processor, but we believe that it will eventually bring persistence into the processor itself. Even registers may eventually be persistent, but that's not right around the corner. So let's talk about where things are today and in the near future. Today, there's a lot of excitement about using an emerging memory in standard computing systems. Not only is an emerging memory attractive as a new layer in the memory and storage hierarchy, like we showed a few slides back, but it also provides a path to interesting architectural innovations. In particular, innovations that solve data motion issues, which are common in a von Neumann type computer. Lots of energy and time are wasted moving data around. These energy and time issues can be addressed by moving from this von Neumann type architecture, where we have very distinct units that we move data around between, as illustrated on the left, to a memory-centric approach as illustrated on the right, which moves towards less data movement, more processing closer to the data. And this opportunity has led to new protocols like OpenCAPI and CXL. These approaches support memory disaggregation by removing some memory from behind the processor. Memory pooling and sharing to more efficiently use storage and memory to address new problem classes, and heterogeneous computing, which allows data to be processed by a variety of types of accelerators. Note that the memory-centric system includes a DRAM connected directly to the CPU. We'll call that near memory. It has lower latency. And a far memory at the center of the diagram. It's labeled SCM memory. SCM in this case stands for storage class memory, so persistent memory of some sort. Since the far memory is shared, its data path to the CPU must be arbitrated. And that adds a little bit of latency, and thus we use this term near and far memory, and that'll be important for a point I'm going to make in just a minute here. Industry is slowly converging on a preferred mix of these solutions to solve today's and tomorrow's problems. CXL is backed by a big consortium and will be a switched memory channel enabling pools of non-heterogeneous memory with various latencies and data rates in storage boxes. And some of these be persistent, some of them not. CXL supports memory and accelerators for resource pooling and allocation. DDR channels, that near memory, will continue to be used for low latency memory, at least through DDR5. And after that, parallel data path, there may be some problems in going to higher speeds. What will happen then beyond DDR5? It may be that higher data rates may drive the use of a lower latency serial interface rather than parallel memory interfaces, at least for applications that need that performance. For memory, the industry appears to be moving towards a specific mix, divided by whether the memory is near memory or far memory. CXL is gaining popularity for pooling heterogeneous memory or memory with mixed latencies and data rates, and the memory on accelerator cards within a box. Gen Z, which is now part of CXL, is likely to be used to connect storage boxes and racks together. Now, this near memory that's the far memory approaches there. Near memory has three candidates in the running: the traditional DDR channels, which should continue to be useful for smaller near memory systems, at least through DDR5, and high bandwidth memory, HBM, which provides more bandwidth than DDR, but it's more flexible, less flexible and more costly. For instance, this is used by NVIDIA's GPUs. They have high bandwidth memory. And then another interface called OMI, which is the open memory interface currently used by IBM's power processors and certain FPGAs. Now let's take a closer look at how these near memory interfaces compare against each other. This chart illustrates the operating spaces of these three near memory interfaces. This is where the fastest data processing is for whatever is being done. The chart here shows DDR4, DDR5, high bandwidth memory, as well as the open memory interface. DDR provides a satisfactory solution for near memory in PCs and smartphones, but it falls short for high-end servers and accelerator cards. Many accelerator cards today, which need higher performance, many accelerator cards today use high bandwidth memory because of its high bandwidth. especially if they can operate in the limited memory space afforded by HBM. It's basically made with stacks of DRAM on top of each other. HBMs are those stacks. They provide 1,000 to 2,000 parallel signal paths. That's where they get the speed from to the processor. This can improve performance, but the processor and the HBM also have to be intimately connected. HBM, the high bandwidth memory, is used in applications that can accept its significantly higher price. Yep, those through wafer visas are expensive in return for its blazing speed. Although HBM is a help, it's considerably more expensive than standard DRAM, and it's only available in stacks of no more than 12 chips, limiting its use to lower capacity memory arrays. Now, this open memory interface, or OMI, uses existing high-speed serial signaling PHYs with a custom protocol to connect the processor to its DIMMs. These differential DIMMs are made of standard low-cost DDR DRAMs in an OMI transceiver chip. OMI can provide near HBM bandwidth at a DDR-like capacity and price. Now, another interesting development is this UCI, Universal Chip Interface, Interconnect Express. It's a new standard for connecting 2D planar, basically, and 2.5D, that is a little bit of chip stacking, chiplets in a system-on-chip package. Uses range from SoCs for handheld devices to high-end servers. This UCIe standard permits mixing and matching dies from multiple sources with different packaging options. UCIe combined with CXL through a UCIe retimer allows extending off package to connect with other media, for instance, optics, electrical, or microwave, that's communication media, in order to access memory, storage, and processing pools. Going to 3D integration, that is where we're really stacking wafers, chips on each other, often called heterogeneous integration, would create stacks of interacting chips, providing even denser compute packages with less data movement and lower latencies. And these are also on the horizon, even going beyond that 2D and 2.5D system-on-chip packages. So we talked a bit now about what's driving these changes. We talked a bit about the computing architecture changes. Let's take a look at the memories themselves, these non-volatile memories that are going to help remake the ways that we do computing. There are many emerging memory types. They're vying essentially to replace NOR flash at the least. All share the same attributes. They all have a small single element bit cell that promises a scale smaller than current technologies in order to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write in place with no need for a block erase, as in flash memory. And they have more symmetrical read and write speeds. Finally, they're all non-volatile or persistent. Data doesn't disappear when power is lost. They can all be used as persistent memory. New memories are necessary for Moore's law scaling to continue. These technologies include ferroelectric RAM, that's random access memory, MRAM, magnetic random access memory, resistive RAM, and phase change memory, like the Intel Optane memory that we discussed earlier. Let's talk about MRAM first. It's shipping today, but in relatively low volumes. Over the history of the technology, Everspin, the company that's shipped the most of these standalone MRAM chips, has shipped over 120 million of these chips. The company has a partnership with Global Foundries. They're building 300mm wafers for Everspin, but they also license the MRAM technology from Everspin, and they're offering it to other customers for embedded memory applications and system on chips. We've listed some high-profile applications for Everspin's MRAM here. Another company, Renesas, is shipping an MRAM chip that it inherited through its acquisition of IDT. Other foundries are now offering an MRAM option to their SoC clients, including Global Foundries, TSMC, Intel, Samsung, as well as others. Phase change memory, 3D crosspoint example of that, is another technology that is shipping in volume. The most widely known example is the 3D crosspoint, and sold as Optane SSDs and DIMMs by Intel. It builds on technology that Intel has had in development for over 50 years. Their first Optane SSDs shipped in 2017, and the first DIMMs shipped at the end of the following year. Both are currently used in storage systems and other computing applications. Intel was using Micron Technology as its manufacturing partner for this technology, but Micron decided to exit this business last year and sold the plant that it was using to make 3D crosspoint. In addition to this Intel and former Micron effort, ST Microelectronics currently produces phase change memory-based microcontrollers for automotive applications. Resistive RAM is our third technology. It's also in production and for discrete devices, but in a very quiet way. It has been shipped by Adesto, now a part of Dialog, since 2013. Dialog plans to license its CB-RAM memory technology to global foundries to be offered as an embedded non-volatile memory option on its 22FDX platform and in future platforms. ARM announced that the spin out of Surfy Labs to develop and license new types of non-volatile memories based upon correlated electron materials, or CERAM, in a joint development project with Symmetrix Corporation. Other companies currently ship resistive RAM into both commercial and military and aerospace applications, and leading foundries are supporting resistive RAM as another alternative to embedded NOR flash. In fact, if we look at the list of foundries we talked about earlier, many of them are also offering a resistive RAM option in addition to MRAM. Now, finally, we come to the oldest emerging memory technology, ferroelectric memory, or FRAM. Surprisingly enough, this technology predates the development of the integrated circuit. The photo on this slide was published by Bell Labs in 1955. It shows a single SBT crystal with vertical and horizontal metal traces to connect with it, and it was meant to be used as a non-volatile memory. From the perspective of unit shipments, FRAM has also shipped more than all other emerging memory technologies combined, because it's found its way into over 4 billion chips. It's most commonly used in RFID cards, thanks to its extraordinarily low write energy requirements. When using harvested energy, you want to something to be able to write without using a lot of energy. Until recently, FRAMs were based on unfriendly materials such as lead and bismuth that most semiconductor fab manufacturers resisted putting into their factories. But in 2011, NAM Lab in Dresden, Germany, found that a crystalline form of hafnium oxide has strong ferroelectric properties. This created new life for ferroelectric memory, and hafnium oxide is commonly used as a high-K dielectric in leading-edge CMOS processes. Fab managers understand how to make it in high volumes. Besides its use in ferroelectric memories, this type of hafnium oxide is also being investigated for other interesting applications, for instance, put into DRAMs. Researchers have used it to produce a 3D DRAM similar in process to standard 3D NAND flash, for example. So let's look at who's making these emerging memory technologies. So leading foundries, those processes finer than 28 nanometers, now are offering emerging memory technologies to their customers. These foundries include TSMC, Samsung, Global Foundries, Intel, UMC, and probably others as well. They're offering spin tunnel torque MRAM today, but they're planning on offering spin orbit torque, or SOT MRAM, and other MRAM technologies in the future. Those are capable of working faster and also operating at lower energy levels. Although today's products aim to replace embedded NOR flash, newer technologies can compete against SRAM and are already being used to displace some higher level SRAM today, as we'll talk about in just a few minutes here. And other companies, and possibly even DRAM down the road. And we'll show how the unit volumes could get to those levels where that might be possible. Other companies offer resistive RAM and also ferroelectric RAM today. Now let's look at some applications that are already using these emerging memory technologies. We're going to start off with IBM's FlashCore module. It was introduced in 2019, and they're the storage modules used in the company's Flash Systems family of products. The FlashCore modules are now available with storage capacities up to 38.4 terabytes. Everspin MRAM chips are used for write caching in these SSDs, journaling to keep logs, and also for data buffering. The FlashCore modules use QLC flash memory for the mass memory, the mass storage. They're using the MRAM cache to reduce the write wearing on this QLC flash memory, which has lower endurance than, say, MLC flash. The products are, or even TLC flash, the products are said to have twice the endurance of standard NVMe SSDs. Over 200,000 of these flash memory modules have been shipped with total storage capacities, this is mostly the flash, of hundreds of petabytes. The latest FlashCore modules allow some processing in the SSDs, and essentially they're moving into this state of computational storage, which is becoming very popular and may have some interesting implications also for computer architectures. These online processing right now in these devices, including compression and decompression, which can increase the effective storage capacity. It's done totally inside the drive itself. Many more computational functions are planned. And also the latest generation, Gen 3 of these flash core modules have RISC-V core built into the processing units that could assist in analytics and machine learning applications. So this is a block diagram of a company called Ambic's fourth generation Apollo system on chip, which serves as both an application processor and a coprocessor for ultra-low power battery operated IoT endpoint devices, for instance, smartwatches. If you look at the lower left corner, you'll see the system memory subsystem, which is made of MRAM and SRAM. The chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM. Another device that ships today with embedded MRAM is made using memory technology by a company, IP, by a company called Newman, which is an MRAM IP house. This chip is used by NASA for remote computing in space. The MRAM is naturally less sensitive to radiation than flash memory or DRAM. Its high endurance and non-volatility as well both help to reduce energy requirements and for extended use in a harsh environment like outer space. Each deep neural network accelerator chip that these has from 1 to 32 processing engines, 32 to 1024 ALUs to perform efficient processing for matrix multiplication, convolution, etc., in order to allow these devices to make decisions on things to do in space with a spacecraft. MRAM is also being used in Sony's GPS receiver, which can be found in Huawei's GT2 smartwatch. Built on Samsung's 28 nanometer FD-SOI process, this IoT endpoint includes 8 megabits of embedded MRAM. There are many other emerging memory devices that ship in production today. This includes an MRAM microcontroller from NXP, a phase-change memory-based microcontroller from STMicroelectronics, and an FRAM-based microprocessor from Texas Instruments, and also from Fujitsu. With all these devices coming online, what's our outlook for the future of this market? This is one of the key parts of this emerging memory report that my colleague Jim Handy and I do every year. And this data comes from our last report. We're working on the new report now. That report was called Emerging Memories Take Off. It shows that the total emerging memory market we're projecting that, including MRAM and also Optane memory, could exceed $44 billion by 2031. This chart shows how the petabyte shipment growth could drive that number. The figure compares the current and projected capacity shipments for the next 10 years for various emerging non-volatile memory technologies, here exemplified by MRAM and 3D XPoint versus DRAM and NAND flash. Now, the assumptions from this chart are that the 3D XPoint is adopted widely by Intel customers and Xeon servers, that embedded MRAM replaces most system-on-chip NOR and SRAM, and that MRAM has strong appeal for these mini AI applications. Note that MRAM shipment growth in this chart includes both standalone as well as embedded MRAM technologies. So summary, NOR flash SRAM stopped scaling, DRAM scaling has slowed. It's getting harder to make smaller memories, and that is leading to an opportunity for new non-volatile memories, which could fill that void. Particularly the big attractive opportunity right now is going below 28 nanometers for code storage on embedded devices. And that's going to lead to new memory-centric compute. These changes are leading to new types of connectivity, new ways of disaggregating, new memory-centric computer architectures that could be used for artificial intelligence and other data-intensive operations. That's going to change the storage and memory hierarchy, the way that we use different sorts of technologies. And there's 4 leading candidates for these emerging non-volatile memories: MRAM, phase-change memory, resistive RAM, and also ferroelectric RAM. And leading foundries are already supporting these new memories. There are initial products are out there today. MRAM, and so we're projecting that MRAM and phase-change memory revenues could exceed, again, $44 billion by 2031. Just a little bit about the report. If you're interested, it's now available. This is the latest report we have out. And a lot of this information in this presentation was drawn from this report. It describes the entire emerging memory ecosystem: phase-change memory, resistive RAM, magnetic random access memory, and ferroelectric RAM. Talks about the company's markets, support requirements, examines emerging memory consumption, both for embedded and discrete devices. It's 230 pages with 36 tables and 155 figures. If you're interested in this, there's URLs at the bottom of this slide where you can check the report out. There are some references referring to SNIA, CXL, OMI, and also our report, of course. And I want to thank you very much. And if there's time, I'd be glad to take some questions.
Yeah, let's see if we can take some questions from attendees. You could put, I believe attendees could put some questions in the chat window, or we can save that for our panel discussion.
There also apparently is a Q&A window, but I don't see any questions.
Yes, you're right. There's a
but I don't see any
window.
questions in there right now.
Okay, so